Hello and welcome to this video about alcohols for A-level chemistry. In this video we will be looking at how we classify alcohols, including how we name them. We'll be looking at the different methods of producing alcohols, and then we will move on to the different reactions of alcohols, focusing primarily on the elimination reactions and the oxidation reactions. In one of my other videos, I go into greater detail about how you name alcohols, but I'm going to give you a little bit of a review now. So first up, alcohols have got the general formula CN(H₂N + 1), and then OH to finish it off. And what that means is if we have got 2 carbon atoms, we need to double it and then add 1, so 5, and that's how many hydrogen atoms we have. And then we have the OH on there. Now, the formula could be expressed as C₂ₙ That is slightly more tidy, but it is less helpful because writing it with the OH group like this gives you the knowledge that this is an alcohol, because the alcohol functional group is a carbon atom connected to the OH group, sometimes simply written ROH. In terms of naming alcohols, if we take a look at these 2 alcohols here, first of all, how many carbon atoms do they have? They've got 4. So this is going to be butane. Then we need to look at where the position of the alcohol group is. We always try and keep the numbers as small as possible, so I'm going to start numbering from the right-hand side here. And so the alcohol group is on position number 1, and so we call this butane 1-ol. On the second example, we have to start numbering from either end. If I start numbering from the left-hand end, this will be carbon number 1, 2, 3. If I start numbering from the right-hand end, 1, 2. So there isn't a rule for which end you have to start from, except you have to start from the end that keeps the numbers as small as possible, which means that you have to do a little bit of working out when you've been presented with the example. So this is now a chain of 4 still. So it's butane. This time the hydroxyl group, the alcohol group, is on position number 2. So it's butane 2-ol. In this next example, we have got a chain this time not of 4, if I circle it. The longest chain that you can make is a chain of 3. And so this time it is going to be propane, and it will be 1, 2, 3. Propane, the group is here, 2-ol. But we have got this group on here, and it's a methyl group because it is a chain of 1 carbon atom. So this is methyl propane 2-ol. You could be tempted to call it 2-methyl propane 2-ol. If this was an exam question, you would see that written in brackets like that, because the 2-methyl is actually unnecessary. The methyl group couldn't be on any other position, because if it was on position number 1, it wouldn't be propane 2-ol, it would be butane 2-ol, and that would be the same if it was on position number 3. If we work out the formula of each of these alcohols, we will find that, in fact, all 3 of them have got 4 carbon atoms. They have also got 9 hydrogen atoms, and then they have got their OH group, or C₄ₙ And what that means is that these 3 are all isomers of the same formula. They've got the same parts, they're just arranged slightly differently. So that means that they are structural isomers. And in fact, these 2 at the top, they are position isomers, and this bottom one, and either of the 2, in fact, would be considered to be chain isomers. I'm going to just give you 2 slightly more tricky examples about how you name alcohols here. First up, I mentioned that alcohol groups can sometimes also be called hydroxy groups, and this is a prefix that we give to alcohols if they are not the most important group in the molecule. So, in other words, if there is something of a higher priority. I explore this in greater depth in my nomenclature video, But what we'll do for now is if we say that this group here, which is a carbonyl group on the end of a chain, which makes this an aldehyde, and aldehydes are a higher priority than alcohols. So this makes this molecule an aldehyde. It makes it an aldehyde with 2 hydrogen atoms in it, which makes this ethanol, but we've got this OH group in there as well. So that means we've got 2 functional groups. So this becomes hydroxy ethanol, and we need to give a position for the hydroxy group, and that is position number 2. So this becomes 2-hydroxy ethanol. The second complicated example I want to look at is if there are 2 alcohol groups in the same molecule, such as in this example here. The first thing we need to consider is how long is the carbon chain, and the answer is 2. So this is ethane. Now, because there are 2 groups, this becomes a diol. And so it's a diol. So this is ethane diol, but we need more details on here. We need, first of all, the details of the position, because it is possible to have the diol group on the same carbon atom, but we don't here. So we've got carbon atom number 1, carbon atom number 2. So this is 1,2-diol. And one last absolutely vital instruction on here is if I write what I've written here as my final answer, I get it wrong, because there is one convention in the naming of organic molecules, which is that if the root of the molecule's name, such as the prop, butane, ethane, etc., ends in an N, and then the functional groups part of the name begins in a consonant, then we need to include the letter E. And to say that slightly less scientifically, we can't have 2 consonants one after the other. We need this vowel in between. And that's actually the case the other way around. You can't have 2 consecutive vowels either, so we couldn't have ethane al or ethane ol. And that's why that E gets dropped, and it becomes ethane ol. Ethane 1,2-diol, by the way, is the main ingredient in most antifreezers, which are chemicals that are added to the water in cooling systems in cars and other motor vehicles so that the coolant doesn't freeze when the temperature drops really, really low in the wintertime. I'd like to do a really quick recap about the shape of alcohols here. First of all, we normally represent them in 2 dimensions like this, which strongly implies that this is a 90-degree bond angle between the C₂ₙ bond and the C₂₄ bond, and that's very much not the case. If you remember, anything that is carbon-based will have the same general shape as methane, which is where we've got 4 bonds in the arrangement like that, with all the other groups added on. So this bond angle is more like 109.5 in all of those cases. What is even less accurate is the carbon-to-oxygen bond angle relative to the oxygen-hydrogen bond angle. The way we're representing it here, it looks like it's 180 degrees, and that is definitely not true. So if we consider this from the oxygen atom's point of view, oxygen is in group 6, meaning it's got 6 valence electrons. It's bonded to 2 other atoms, the carbon and the hydrogen. It doesn't have any charge at all, and so the total number of electrons will be 8. We need to obviously divide that number by 2 to get us 4 pairs of electrons, which gives us a starting shape very similar to the tetrahedral shape that I just drew up there from the point of view of the carbon. However, if we track our number of pairs to our number of bonds, we can see that they're different. The oxygen must have 2 bond pairs because it's bonded to 2 different things, which means it's therefore got 2 lone pairs of electrons. And so if I add the H of the alcohol and the CH3 for the rest of the molecule onto here, those are my 2 bonds, and then I need to rub off these 2 remaining bonds and replace them with lone pairs of electrons, which you can just draw as little pairs like that, and sometimes they're written like this, which is the orbital where the lone pair is found. Now, I hope you remember that lone pair repulsion is greater than bonding pair repulsion, and so that has the effect of squeezing these two bonds closer together than they would be if these were 4 bonding pairs. And the effect is a reduction in that bond angle of 109.5 by 2.5 degrees for each of those lone pairs. And so that gives us a final bond angle of round about 104.5 degrees. We're going to return to our 3 examples of alcohols that we looked at earlier to learn about the classification of alcohols. So not only do we describe them as alcohols, they have an additional subclass, and these are referred to as primary and secondary and tertiary alcohols. And I'm deliberately writing them in these positions because each of these molecules is an example of a primary, secondary and tertiary alcohol, and they have these little abbreviations on here, which is a 1 degree, 2 degree and 3 degree is how you would write that. How do we know if something is a primary or a secondary or a tertiary alcohol? Well, it is as simple as finding the alcohol group, here it is in butan 1-ol, looking at the carbon atom that it is attached to, so this one, and seeing how many carbon atoms are attached to that alcohol carbon. So if we have a look here, this is 1 carbon atom that is attached to the alcohol carbon, and the other 2 atoms are hydrogen. So we have got 1 R group. It's this whole thing, in fact, but it doesn't matter really how long it is. So this is a primary alcohol because there is 1 R group attached to the alcohol carbon. If we apply the same methodology to the second one, here is the alcohol carbon. That's the one with the OH group, remember? And this time we have got 2 carbon atoms bonded to the alcohol carbon. We've got 2 R groups on here. They're both different, but that doesn't matter. It's about how many groups there are. And then if we find the carbon with the OH group in the final example, we will see that this time we have got 1, 2, 3 carbon atoms bonded to the carbon with the hydroxy group. And so this is a tertiary alcohol because of these 3 groups attached. And primary and secondary and tertiary alcohols are different in terms of their chemistry, which is why knowledge of whether it is a primary or a secondary or a tertiary alcohol is important, because we can make predictions about how something will react or perhaps won't react. We're going to move on now and take a look at a couple of physical properties of the alcohols. First of all, melting point and boiling point. Now, obviously, melting point is the point at which something turns from a solid into a liquid because you are forcing those particles to go further apart. And that's why I've drawn the skeletal formula of 2 alcohols here, because I want to show that alcohols have obviously got a dipole because the oxygen is more electronegative than the hydrogen, leaving the hydrogen electron deficient. They also have got lone pairs of electrons on the oxygen part of the alcohol group. And what that means is that hydrogen bonds can form between the electron deficient hydrogen and the lone pair of electrons on the neighbouring alcohol group. What this means is we get hydrogen bonds forming between neighbouring alcohols, which means that they have higher melting points than you might expect for a similar length alkane. And so butan 1-ol that I've drawn here would have a higher melting point than butane. That isn't an entirely fair comparison because butanol is heavier than butane, and so if we compare butan 1-ol, pentane and hexane, and here are their MR values, you can see that pentane is very similar to butan 1-ol, and the boiling points of butan 1-ol is 118 degrees C, whereas for pentane it is 36 degrees C, so similar mass, and that hydrogen bond has had a huge difference. Hexane, which is actually a heavier mass than butan 1-ol, it still is not as high a boiling point, and that's because of the alcohol having the hydrogen bonding and the alkane not. They only have the van der Waals forces. Last of all, just another little recap of intermolecular forces. The boiling point of butan-1-ol, as we've said, is 118 degrees C, and butan-2-ol is closer to 100 degrees C, and that is because of the shape of the molecule. In effect, butan-1-ol is almost linear, whereas butan-2-ol has got this branch. So these molecules don't fit together so closely on average, and so they are easier to pull apart, which means that they need less energy to pull them apart, which is why their boiling point is lower. The second property I wanted to look at is the solubility of alcohols. Now, solubility is the ability of something to dissolve in water, and this, in effect, can be reduced down to the ability to form strong interactions with water. In other words, hydrogen bonds. And alcohols are soluble in water because they have the ability to form hydrogen bonds, as we saw on the previous page. And to show that, let's draw the OH from the alcohol group, and then let's draw the oxygen from a water molecule. And let's finish the rest of the alcohol group. Let's make it methanol for ease. Then let's add all the other bits that allow the hydrogen bond to happen. So we're talking about the lone pairs and the electron deficient groups, because often in exams they say show all lone pairs and partial charges, and so it's a good habit to get into on here. And so all that's left is to show the hydrogen bond on here, and just because I'm not particularly good at drawing, I'd like to label it as a hydrogen bond, just to be sure. This is a good little reminder about the bond angle between the hydrogen bond and the other bond that the hydrogen atom has got. It is always 180 degrees, because if you consider this is one pair of electrons, this is another pair of electrons, albeit it's come from this oxygen, so we've got one pair, we've got two pairs. There are no lone pairs on the hydrogen, so the furthest two pairs of electrons can get in three-dimensional space is 180 degrees apart, which is why the hydrogen bond angle to the hydrogen-oxygen bond angle is always 180 degrees. Now, there is, sadly, a complication to this pattern, and that complication comes when alcohols get longer. So the longer an alcohol gets, the less soluble it becomes. And I've drawn octan-1-ol to illustrate this idea. So octan-1-ol has got the alcohol group, of course, and so that can form hydrogen bonding with water because it is polar. However, the rest of the molecule is non-polar, and what that means is it won't be able to interact with the water. And so that means that this part of the molecule will be insoluble, and in fact it's even referred to sometimes as hydrophobic, which means it can't interact with water, and the polar region is sometimes referred to as hydrophilic. And so there comes a point where the hydrophobic part of the molecule is more significant than the polar hydrophilic part, and that means that it will no longer be soluble in water. And I chose octanol because it is at this point that alcohols are considered to be immiscible. In other words, it won't dissolve, it won't mix with the water at all. And that's a gradual change from methanol being very, very miscible with water, then ethanol and propanol similarly, but then bute, pent, hex and hept gradually become less miscible with water, less soluble, up to the point when we get to octanol, when it's considered to be insoluble in water. Alcohols have many scientific, medicinal and industrial uses. They are really important chemicals because they can be used to produce lots of other different organic molecules. Now, in the equilibria topic, you learn how methanol can be produced from methane. And so what we're going to look at here is we're going to look at the two different methods of ethanol production. Ethanol is by far the most important alcohol that we use. It is used in the manufacture of so many different organic compounds. For instance, cosmetics, aftershaves and perfumes, but also drug manufacture, detergents and other things such as inks. Now, there are two different ways of making ethanol, and you need to be able to compare and contrast the two methods. And the first method involves ethene, And as you can see from the ethene molecule, we are missing atoms of oxygen and hydrogen, and so this is a hydration reaction where we add water. Following this process backwards a little bit, ethene is produced when one of the fractions in crude oil is cracked in a cracking reaction. And of course, those fractions were originally derived from crude oil in the process of fractional distillation. And crude oil itself is a fossil fuel formed over a period of millions and millions of years, which means it is very definitely a non-renewable resource. By contrast, there is a renewable method which involves the planting of crops. The crops then grow by the process of photosynthesis, and then the carbohydrates in the crops are broken down in the process of fermentation. This gives us an aqueous solution of ethanol, which then is purified further in one last step of distillation. Now, as I say, this is very much a renewable process because the crops grow relatively quickly compared to the formation of crude oil. Now, it's not all bad news for the non-renewable method though. It is very definitely fast, and by comparison, fermentation is a much slower process. The products of the hydration method are essentially pure, whereas the fermentation process is less so. Even after distillation, you still end up with an aqueous solution of ethanol produced at the end of it that is not 100% pure. Another big difference between the two processes is in fact how they are carried out. The hydration method is a continuous process, whereas fermentation is a batch process. Now that's not necessarily good or bad specifically. Now a batch process is probably best understood if you compare it to something like cooking, where you follow a sequence, there are steps that happen in a specific order, and at the end you have produced your meal or whatever it is that you're trying to produce. And then you start again for the next batch. Whereas continuous, it doesn't work so well for the cooking analogy, but if we try and make it do that, it's a bit like having a big vat of soup on the hob and you keep ladling some out as you need it, but at the same time you're adding fresh ingredients to the soup as you go on through. So a continuous process never really stops or rarely stops, and you're continuously taking some of your product out at the same time as putting new reactant in. You don't need to know any of the nuances of continuous methods and batch methods, you just need to be able to appreciate that they are different approaches. So these are the main differences between the two processes. If we explore hydration in a little bit more detail now, this is the overall equation where you can see that we've got our ethene molecule as one of our two reactants, and the water adds across the double bond to give us our ethanol. Now it is absolutely essential in this process that we have a phosphoric acid catalyst. Phosphoric acid is H3PO4, and without the phosphoric acid catalyst this basically just wouldn't happen at a speed that was financially viable. Now I want to show you the mechanism for this reaction, but I don't think you're going to be asked it in the exam, it is just for your appreciation. So first of all, the H plus from the phosphoric acid catalyst attacks the double bond. This is really similar to the first step in an electrophilic addition reaction. This gives us a carbocation intermediate, which is vulnerable to attack by the water because it is electron rich with a lone pair, and so it attacks the carbocation. This is similar to the nucleophilic attack, and it's also similar to how a halide ion attacks a carbocation in electrophilic addition. And then in the final stage, we have got this oxygen, which is now positively charged because it's got too many bonds, and so the final step is the electrons from this oxygen to hydrogen bond go back to the oxygen. And this is similar to the ammonia nucleophilic substitution reaction, where the nitrogen has its charge restored by losing a hydrogen. And at the end, as you can see, we have got the ethanol, that has been produced, and we've also got our H+ back, which shows that this was acting as a catalyst because it was present at the beginning from the phosphoric acid and it is present at the end, so it can be reused. If we move on now to take a more detailed look at fermentation, the glucose from crops such as sugarcane or sugar beet are made into an aqueous solution with the enzymes from yeast, and this then produces ethanol and carbon dioxide. And this of course needs to be balanced. We need 2 ethanol and we need 2 carbon dioxide. And this is the anaerobic respiration of the yeast. And so yeast as a biological organism is affected by temperatures, and so we want the reaction to be as fast as possible, so we want a high temperature. However, we have to settle for 35 degrees C because the enzymes are denatured, they become ineffective if the temperatures get too high. It's very important that this reaction is carried out under anaerobic conditions, and this means no oxygen. If there was oxygen present, the ethanol produced would be oxidized and it would produce ethanoic acid. Now, we're obviously talking here about an industrial scale fermentation process, but this can happen at home if anybody is trying to home brew some alcohol. You can get the ethanol produced, which is the alcohol that people would drink, but if it gets exposed to oxygen for too long, it can kind of turn sour and therefore be less palatable. And this is a small-scale example of one of the dangers of fermentation going wrong on a big scale in industry. The last step in this process is distillation. I mentioned earlier it's to remove some of the ethanol, but it isn't just that. Once the ethanol concentration in the reaction mixture gets above 15% or so, the enzymes stop being able to function, and so fermentation actually stops anyway. And so distillation separates the ethanol from the water. And ethanol has got a boiling point of 78 degrees C, and water, as we know, has got a boiling point of 100 degrees C. So as we warm these two chemicals up, the ethanol will boil first, and so the ethanol can be removed, provided we keep the temperature below 100 degrees C but above 78, so let's say 85 degrees C. We will evaporate off the ethanol but not the water, and then we will condense the ethanol in a different part of our distillation apparatus. Another really important difference between the production of ethanol from ethene and the production of ethanol from fermentation is the concept of carbon neutrality. Now, carbon neutral is to do with the carbon footprint, which is to do with the net carbon output from a particular process. Now, if something is carbon neutral, this means that the carbon dioxide taken in during a process is equal to the carbon dioxide released during the same process. And that's a really, really important concept. If we consider the main implications for this topic, we are talking about the process that takes in carbon dioxide being photosynthesis as the crops grow, and then the carbon dioxide released during the process would be fermentation of the plant sugars, and then combustion of the alcohol that is produced, because the alcohol that is produced, the ethanol, is considered to be a biofuel, which means it's a fuel derived from biological material, in this case, plants. To put that into a potentially slightly more easy to understand terms, if we consider the process where carbon dioxide is taken in during the production of ethanol, that is photosynthesis. And this is the equation for photosynthesis here. 6 carbon dioxide molecules go in to the production of 1 molecule of glucose. And then if we carry out fermentation, anaerobic respiration of this 1 molecule of glucose, we will make 2 molecules of ethanol, and 2 molecules of CO2. Then the ethanol that gets produced is most commonly used in combustion reactions. And so when those 2 ethanol molecules burn, they react with oxygen. They're going to make carbon dioxide. They're going to make 4 carbon dioxide to balance this equation. And they're also going to make water. And because we've got 2 lots of 6 hydrogen, that makes 12 hydrogen. That means we're going to need 6 water molecules over here. And we've got 4 times by 2 makes 8 oxygen. 6 times by 1 makes another 6. So that's 14 oxygen atoms in total. We've got 2 oxygen atoms in our ethanol already, and so to balance this we need a 6 on there. And what I hope you can see here is actually these 3 processes completely cancel each other out. Let's focus on the carbon dioxide though, because that's the most important thing for carbon neutrality. We had 6 carbon dioxide coming into the process, 2 carbon dioxide molecules were released during fermentation, and then a further 4 carbon dioxide molecules were released during combustion. So that means that the CO2 in during photosynthesis is equal to the CO2 out during fermentation followed by combustion. The other molecules also cancel each other out to a no overall change. So at face value, this looks like it is carbon neutral. Now that's not completely true, because the process of fermentation and the transport of the crops and all those sorts of extra things, they also have an energy requirement, which means that carbon dioxide will be produced as the tractor or the harvester burns the fuel to release its energy. And so, whilst it's not completely carbon neutral, it is significantly closer to being carbon neutral than using the non-renewable method of using fossil fuels and then hydrating the ethene. So carbon neutrality, something to aim for. We are very close to it, but we're not quite there yet. Probably the closest you could get to being truly carbon neutral is growing the crops on your farm, harvesting them by hand, processing them by hand, and then burning the ethanol on site. And so you never had to transport any of your crops, you never had to use any fuel to transport the ethanol that you had produced at the end of it. Elimination reactions are one of the 2 main alcohol reactions that you need to know about for A-level chemistry. We first come across elimination reactions in the halogenoalkane topic, where a halogenoalkane is converted into an alkene. For alcohols, this is really similar. Elimination reactions are reactions where a small molecule leaves a parent molecule. Now for halogenoalkanes we lost hydrogen chloride or hydrogen bromide, but for alcohols always lose H2O, and the OH is always from the alcohol group, and the H is from a carbon next to the alcohol carbon. And so, for instance, here in butan-1-ol, you can see that we have got the OH group on the end here, and the H that we're going to remove along with that to make it H2O has to come from one of the adjacent carbons to the alcohol carbon. Now, there is only one adjacent carbon to the alcohol carbon in this case, and so the hydrogen that gets to be removed is either this one at the bottom or the corresponding one at the top. But there is no difference between them because the bonds can rotate around, so we will remove these 2 groups of atoms. And as you can see, this is what we end up with. We've lost our water, and we end up with the alkene but-1-ene, because the alkene is in the position between carbon number 1 and carbon number 2, and our second product is water. And because our second product is always water, this reaction is known as a dehydration reaction as well as an elimination reaction. Now, to make this reaction happen, you need to subject it to quite strong heat, 600 Kelvin, and we need to use a catalyst that is most commonly an aluminium oxide catalyst. Now, to do this experiment in a lab is actually really similar to doing the cracking experiment in a lab. You have a trough full of water with an upturned tube containing water, And then we've got a boiling tube on its side made of some more heat resistant material than regular glass. You have your aluminium oxide catalyst here, and you have got your alcohol at the end here soaked on some ceramic fibre. So what you do is you heat the aluminium oxide catalyst here. You don't heat the alcohol directly, but the warmth from the heating of the catalyst will make the alcohol vaporize, and then the alcohol vapors will pass this way, and then they will react in the presence of the aluminium oxide catalyst, and then they will be dehydrated and turn into the alkene. And then the alkene will drift down here through this delivery tube into the water, and then it will come out here as bubbles of alkene gas. And then the gas, in this case but-1-ene, will collect at the top of the tube here, and the water will be displaced. It will be pushed downwards by the presence of the extra gas at the top of the tube. And in exactly the same way as with the halogenoalkane experiment, you can use bromine water, which is just Br2, which is a yellow-orange colour, and you can mix it with the alkene and you can shake, and it will decolorize in the presence of alkenes. And that has proven that there is an alkene present. If you've got your yellowy orange and it goes colourless, that's what we mean by decolorize. It loses all of its colour and it becomes colourless. And last of all, you might be required to write an overall equation for this process. So if we just pick ethanol, just because that's a little bit easier to write and I can fit it into this space, there is our ethanol, and it is going to turn into ethene and water. Over the arrow, let's add our temperature and our catalyst again. Now, for A-level chemistry questions, it is more likely that you will be asked about elimination using a concentrated acid catalyst. And so this acid-catalyzed elimination normally happens using concentrated sulfuric acid, but you could alternatively use concentrated phosphoric acid, or phosphoric 5 acid as it is often called. As we showed on the previous page, you need to be able to write equations for the dehydration of alcohols, but a second thing that they could quiz you on in an exam is they could ask you to write the mechanism for this. And so here is our ethanol, and this alcohol is going to undergo acid-catalyzed elimination. You're always going to be asked to draw the mechanism for the acid-catalyzed elimination, and just to remind you, what I'm about to draw in blue, this is the thought processes, not what you'd write in an exam. So the alcohol has a polar bond. You don't have to show the poles. You do have to show the plus charge on the hydrogen ion. That is absolutely essential. And you do have to show the lone pair of electrons on the oxygen that is going to be used to accept that proton. So what I've shown in red there is absolutely essential. Same as the green, the blue is just the thought processes that show why the oxygen atom is attracted to the hydrogen ion. And then we have our intermediate molecule that forms once the oxygen has accepted the proton. I've missed something off here deliberately so I can help you to understand the process. If we've got a hydrogen ion in the reactants at the beginning that is positive, and if our other reactant has no charge, we cannot have a second stage where the whole molecule here has no charge. The molecule has to be positive, and it makes sense that it would be the oxygen that needs to be positive. And the reason that the oxygen needs to be positive is it has used 2 of its own electrons to form a new bond to this hydrogen, a dative bond to this hydrogen atom. So it is in effect sharing its electrons unevenly with the hydrogen, and so that leaves the oxygen slightly electron deficient, which is why we've got a positive charge, because this hydrogen on here has got an extra share of the electrons that the oxygen had. Or you can just think about it mathematically, that the hydrogen was positive, it's gained some electrons, so the oxygen now must be positive in return. So that will cost you a mark if you drop that positive charge on the oxygen. The final arrows are really, really similar to the arrows in elimination with halogenoalkanes. We have got the leaving group, which in this case is the oxygen, and that arrow shows the oxygen taking its electrons from the bond to the carbon. That's the same as in the halogenoalkane, where the halogen takes the electrons from the bond with the carbon. And then again, an identical arrow is where the electrons from a carbon to hydrogen bond move into the space between two of the carbon atoms and leave us with a double bond. You never have to show what happens to that hydrogen in terms of any curly arrows. And then our final product over here is the alkene. It's lost the water. Here is the water that it has lost. And nicely, here is an H+ ion that has just been kicked out of this carbon atom over here. And the good news is we had an H+ ion at the beginning, we've got one back at the end, and this is why the acid is considered to be a catalyst, because we have regenerated the H+ ion. Now, in an exam, you are unlikely to be required to show this final step unless they say show clearly the formation of the organic product, and they're unlikely to ask you for that structure in the exam. But do be aware just in case they do. In that previous mechanism, I was using a primary alcohol, and primary alcohols are nice and easy in that you only ever make one dehydration product from the elimination reaction. Secondary alcohols, on the other hand, produce a mixture of alkenes, and it varies how many they produce. So I'm just going to put 2 or more alkenes on here for secondary alcohols. And let me use butan-2-ol that I've got here as an example. So obviously we are dehydrating this molecule in the elimination reaction. So we are absolutely removing this OH group on here. In terms of which hydrogen atoms we remove, let's start with the easy one. I could remove this hydrogen atom on here. And this hydrogen atom is obviously the equivalent of this one and this one as well. So I'm going to remove the bottom one, and so that's going to combine with the OH group. So let's call this the yellow path. And if I follow the yellow path through to its completion, we are going to end up making an alkene between the first and the second carbon atom in the chain. And so what I'm going to make is I'm going to make but-1-ene. So that is alkene number 1 that it is possible to make. If we then look to the other side of the OH group, I could have removed the blue circled hydrogen atom on here, or its partner up at the top. And so if we remove that blue hydrogen atom instead of the yellow hydrogen atom, and so the water ultimately is coming from this OH group and that hydrogen atom, what we're going to make is something that is actually significantly different in terms of the sequence of atoms. So we have got our double bond forming not between the first and the second carbon atoms that we had in the yellow, and so remember that was but-1-ene because carbon atom number 1 was where the double bond began. This is going to be but-2-ene because the double bond begins on the second carbon atom and finishes at the third, so we call that but-2-ene. Now, if you remember my alkenes video, you will recall that I said that it is a really good idea to get used to drawing alkenes in their correct spatial arrangement. And the reason for this becomes obvious when you see what I'm doing here. If I do but-2-ene in its correct spatial arrangement, showing the 120-degree bond angle approximately between each of the bonds, you can, I hope, see that this is not just but-2-ene, this is Z but-2-ene, because the highest priority groups, the methyl groups here, because they have a higher atomic mass, or the carbon has a higher atomic mass than the hydrogen, they are on the same side. They are zusammen, which means together. And that will, I hope, prompt you to recall that there is an alternative. I could have had the heavier methyl group up at the top on the right-hand side and leave the left-hand side exactly as it was. And so this would become E but-2-ene because the high priority groups are on opposite sides. And so on this occasion, the dehydration of this particular alkene has led to 3 isomeric products. And I have seen exam questions that ask for you to recreate the production of butanene, maybe via a mechanism, and then have a follow-up question about further isomeric products using the EZ isomers as well. So this makes 3. And the final thing that I want to say about elimination is about tertiary alcohols, because tertiary alcohols can also be dehydrated, and this usually produces a mixture of alkenes as well. You might think it's strange me taking the time to mention that tertiary alcohols can be dehydrated, but that's quite leading when we move on to our final section of this video about oxidation, because tertiary alcohols can't be oxidized. And that's something that's often the focus of an exam question. Draw the structure of an alcohol that can be dehydrated into an alkene but can't be oxidized. Let's begin by reiterating what I've just said. Oxidation is the addition of oxygen and the loss of hydrogen or the loss of electrons. All 3 of those are separate definitions of oxidation. They don't usually all happen at once, but it is very common for oxygen to be added and also for electrons to be considered to be lost. Often the electrons definition and one of the other 2 are satisfied at the same time. So I just finished the previous page by saying that tertiary alcohols cannot easily be oxidized, and that's absolutely true. And the reason that I'm saying easily oxidized is that combustion is actually a type of oxidation because the molecules that burn are reacting with oxygen, and all alcohols burn. So technically they can all be oxidized by burning them, but that completely breaks up the molecule. So that's not the type of oxidation that I'm going to be considering from here on in. And from that point of view, tertiary alcohols can't be easily oxidized. Secondary alcohols, on the other hand, can, and they oxidize to form a family of chemicals called ketones, which we'll learn more about in a moment. Primary alcohols, they can oxidize to aldehydes, which can themselves be oxidized further to carboxylic acids. Or, if you get the conditions harsh enough, you can oxidize a primary alcohol all the way through to carboxylic acids. And we're going to explore these in greater depth now. We're going to move on now to take a look at the experimental details first of all. And we'll start with the formation of aldehydes and ketones. And the formation of aldehydes is most commonly the subject of Year 1 oxidation questions. Now, I'm not very good at drawing, and I should say that from the start because there'll be lots of other people out there not very good at drawing as well. And the bad news is you sometimes are required to draw the apparatus for this experiment. So I'm going to take you through it now just to show you how bad a picture can be whilst still getting you all the marks. So, first of all, our chemicals are usually put into a pear-shaped flask. And this will be our reaction mixture. It will have our alcohol that we're going to oxidize. It will have the oxidizing agent, which is potassium dichromate. That's its formula, but I've written the name up at the top. Also going into the mixture will be some dilute sulfuric acid, without which this oxidation just would not happen. And that's the final reagent, but we would put into here some anti-bumping granules. And anti-bumping granules ensure that boiling is not too violent. They make sure it is smooth boiling. It's called anti-bumping granules because bumping is the rapid formation of vapours which can then cause significant harm or damage to the apparatus. Now, because we don't like to draw Bunsen burners, we generally will draw a big chunky arrow like that and write the word heat. And that's what you'll see in most textbooks. However, exams are a little bit fussier than most textbooks, and they want you to be aware of the fact that alcohols are very, very flammable. And so to overcome that, we would actually not heat the alcohol directly, but we would have a water bath. And so this water bath is a safety feature that means that the alcohol that is flammable is not heated directly. And so our reaction mixture gets heated gently, and so it will start to evaporate because the reaction will be taking place above the boiling point of either the reactants or, in fact, hopefully, the products. And so obviously we need to make sure that we don't lose any of our products. So I'm going to draw this next bit live so you can see that it doesn't need to be super quality, and it just needs to capture the core ideas of the apparatus. It doesn't need to show all the connections and all the stylized diagrams. So first up, we've got this for the thermometer. Now the thermometer needs to catch the temperature of the chemicals that are moving into the condenser, and so I'm going to draw my thermometer in here. You're not always required to draw the thermometer in at the top here, but I've done it on this occasion to make sure that you guys note the height of the thermometer in terms of what's happening on the journey of these chemicals, because obviously the chemicals will rise up here and then they'll move sideways, and we want them to hit the thermometer on their way through, on their journey, to make sure that we know what temperature the gases are at as they move into the condenser. Now obviously if you don't include your thermometer, you do need to close the top just with a plug or a bung, because otherwise the chemicals would just rise straight on up out here, and we of course don't want that. Everything would escape. Now the next thing is the condenser. Now the condenser, obviously its job is firmly implied by the name, and so I'll just draw the water jacket around it. And so without this water jacket, you would lose this mark on here. The water jacket does not need to be brilliant. What is really important about the water jacket is that the water comes in at the bottom and goes out at the top. And the reason for that is if it was the other way round, we would end up with a portion of the condensing jacket that was not full of water. And so the water must go in at the bottom and out at the top, because what that will do is it will gradually fill more and more and more of this jacket up with water, and only once it's totally full with water will the water come out of the top. Of course, the plan is that our vapours that have travelled through past the thermometer will gradually condense, and then they'll turn back into a liquid, and they will dribble along the bottom of this Liebig condenser, and once they reach the end of it, they will come out into our collection flask. And I'm just going to literally continue it on like this, and our collection flask will be maybe a boiling tube, and we will get drips of our oxidation product at the end, which, as I said before, this is for the aldehyde or the ketone formation. Now, often it's the case that they ask you, how are we going to maximise the yield of our products? Now, you've got a number of options. The biggest option is to make sure that the vapours are well and truly condensed and we don't get any immediate evaporation again. And so the way to do that is to have a beaker of ice, and the ice will make sure that nothing evaporates, and any vapours that were in danger of coming out and maybe escaping over the side here, they have a second chance to condense. So we have an ice bath at the end. And I guess what we could also do is we could just have a longer tube on here to make sure that nothing has got as much chance to escape on there. So the ice bath is going to maximise the yield. So this is a distillation apparatus, and this allows us to separate the product from the reaction mixture. And this works because the strongest force between aldehyde molecules is dipole-dipole attractions, and those are not as strong as the strongest force between alcohol molecules. Alcohols are held together by hydrogen bonding between their molecules, and that's much stronger as an intermolecular force than dipole-dipole attractions. And so, as such, the alcohols will have a higher boiling point, and so that means that the aldehydes will be the things to evaporate and travel through the tube and collect at the end. If you keep heating this and get it hot enough, provided the water bath allows it to get above the boiling point of the alcohols would collect later, and so you could collect them in a separate tube if you wanted to. We're going to move on now to look at the experimental apparatus that you would use to make a carboxylic acid. Now this is referred to as full oxidation, because unlike with the aldehyde formation, you heat it and oxidize it as aggressively as you can to make sure all of your product is carboxylic acid as opposed to prioritizing the aldehyde. Now, there are some big differences between these two methods, but the subtle differences, first of all, are that the alcohol is used in the presence of concentrated sulfuric acid, and we have an excess of potassium dichromate, and obviously we're refluxing instead of distilling. So those are the subtle differences. The biggest differences are the reflux itself, because whilst you're using a lot of the same apparatus, they are set up totally differently. So you have got your pear-shaped flask. Again, remember I said I wasn't very good at drawing, there we go. And we will have the condenser vertically in the pear-shaped flask. And the water comes in at the bottom and comes out at the top, as we can see here. And then, in a sense, everything else is identical. We have our reaction mixture here. We would heat the container, and it would be safer to use a water bath on this occasion, but depending on the boiling points of the chemicals, you might elect not to, because the reflux does need to get very close to the boiling point of your reactants. So as I say, I'm not great at drawing, but what I've drawn here would be absolutely fine in terms of getting us all the marks, except for labelling our reaction mixture. And I suppose I haven't yet put in the anti-bumping granules as well. And the purpose of doing a reflux is that it allows you to carry out a reaction at the boiling point of the chemicals without losing any of the reactants or products. So it allows you to be aggressive without risking losing any of your product and lowering your yield. So if we imagine that we've heated this and we've got it so hot that some of our reactants evaporate, it will rise up the condenser, and because water is going in at the bottom and out at the top, it's very cold at the bottom, and so we're going to get condensation happening immediately. Some of it might be so hot that it rises higher up in the tube, and this space around about here, that's your absolute maximum about where you'd want condensation to occur. If condensation is happening above that, or if some of your chemicals are escaping out the top, you're absolutely heating it too much, and so we need to turn down the heat or even move it away momentarily, because we want condensation ideally to be happening around about this position on here. And then of course the vapours will drip back down into the reaction mixture and have a second chance to be oxidised. Whilst this definitely increases our yield, it does take a while. You would probably want to reflux for at least 20 minutes in this instance. Now, once you have refluxed for about 20 minutes, you would then distill your chemicals by rearranging the apparatus, because what that will allow you to do is that will allow you to separate the carboxylic acids out from any unreacted alcohols or any of the oxidizing agents that you've got left over in your mixture, and you'd collect your distillate, and that would be pure ethanoic acid, hopefully. Now, in terms of oxidation, you could easily be asked to write equations to show the oxidation of one chemical into another. And this will normally involve structural formulae. So here is ethanol, our reactant, and we're going to oxidize that into the aldehyde ethanal. So CHO is the characteristic way of writing the structural formula of an aldehyde. Now, the good news is you don't have to write the formula for the potassium dichromate in the equation. All we need to do is put a capital O for the oxygen that oxidizing agent provides. So for the purposes of balancing equations, that is a single atom of oxygen. Now, we put square brackets around it to represent the fact that it was coming from somewhere else, and that is the end of our reactants. In terms of balancing this equation, clearly we are short of an oxygen on the right-hand side, and we're short 2 hydrogen atoms as well. So water is the final product on here. If we oxidize ethanol to ethanoic acid, you can see why it's referred to as full oxidation rather than partial. So here is the formula of ethanoic acid. Once again, we are absolutely fine using that capital O in our brackets, square brackets, to represent the oxygen from the oxidizing agent. But on this occasion, because we have got a shortage of hydrogen in the products, we must put water in again. And that gives us, by the way, just to keep track, 3, 4, 5, 6, 3, 4, 5, 6, right hand side. So now we've got enough hydrogen, we need to track back and look at oxygen. We have got 3 on the right hand side, 2 here and 1 here, and we've got only 1 in our main reactant, and so we need 2 oxygen atoms from the oxidizing agent. So as I say, this top one is partial, and that makes sense because it only uses 1 oxygen atom, and this bottom one is full oxidation. So both of these have got ethanol as our reactant, and this one on the top makes ethanal, and on the bottom makes ethanoic acid. We could, in theory, do a third equation that takes our ethanal and oxidizes that to ethanoic acid. And if we have a look at the balancing, we obviously need the O for oxidizing agent, and we can see that we have got 4 hydrogen in the reactants, 4 hydrogen in the products, we've got 2 oxygen in the reactants, and we've got 2 oxygen in the products. So this one is in fact already balanced, which is nice. And really the final equation that you could be asked to write is for a secondary alcohol and to show the formation of a ketone from it. So here is propan 2-ol. You'll notice the alcohol is on here, so that's why we've got CH₂ because we've only got 1 hydrogen on the middle carbon atom. And so we need an O for oxidizing agent, and then we're going to make a ketone, and that's going to be CH3COCH3. In terms of balancing, let's just count our atoms. 3, 4, 5, 6, 7, 8 hydrogen, 3, 4, 5, 6 hydrogen in the products. And so it's quite clear that we need water as our second product. Just count up the oxygen atoms, 1, 2, 1, 2. So we're balanced for oxygen. So our propan 2-ol, our secondary alcohol, has been turned into propanone as our product. And just because ketones are a little bit complicated, I will draw the displayed formula of our reactants and our products here, just so you've got that for your comparison. And to finish this off, just want to show you why we can oxidize some things and not others. First up, remember in oxidation we are either adding oxygen or removing hydrogen or both. And so if we consider on the left hand side the ethanol that's shown here, if we're going to oxidize that, we're going to turn that into an aldehyde. And to do that we need to remove one of these hydrogen atoms on here, because what's going to happen is we're going to form a double bond to that oxygen, and we're in fact going to remove this hydrogen atom as well. And so we need to have removable hydrogen atoms, not just on the alcohol, because there's always one on the alcohol, but on the carbon atom that the alcohol is attached to. And so you can see that we can definitely oxidize ethanol because there is a removable hydrogen. In fact, there are 2 removable hydrogens. Similarly, in ethanol, when we're going to replace that hydrogen and turn it into ethanoic acid, that can be oxidized as well because we've got a removable hydrogen. If we move on to propanone, you can't oxidize propanone further because the carbonyl carbon doesn't have any replaceable hydrogens like we've got over here in the aldehyde. So that one can't be oxidized any further. If we then move on to have a look at a tertiary alcohol, tertiary alcohols, the carbon atom that the alcohol is attached to does not have any hydrogen atoms at all, and so that's why that can't be oxidized as well. So the contrast is for alcohols that are primary or secondary, we've got removable hydrogen atoms. For aldehydes, we've got a removable hydrogen atom. For ketones and for tertiary alcohols, there are no hydrogen atoms in the correct place that we can remove to oxidize them. And so that's why we've got that distinction. primary alcohols and secondary alcohols, yes. Aldehydes, yes. Ketones and tertiary alcohols, no, can't be oxidized. We're going to finish this video by taking a look at how we can prove what products we have made. And I'll consider this in greater depth in my organic analysis video, but for now let's just look at the ones that are specifically relevant to these oxidation reactions. So first of all, we have produced, hopefully, an aldehyde. And to test for an aldehyde, we use Fehling's reagent. And we have to warm Fehling's reagent. And hopefully, if we've made our aldehyde, we will see a red precipitate formed with Fehling's. And that gives us a positive result, proving that we've got an aldehyde. Alternatively, we could use Tollen's solution and again warm the solution. And on this occasion, we will see a silver mirror forming. So there's two tests for aldehydes that you need to know. We also make carboxylic acids in this reaction. And for carboxylic acids, we need to add sodium carbonate solution or sodium carbonate powder. Powder actually works better. And what we see is we see effervescence. And that just actually means fizzing, but it's a very nice word, so I like to use the word effervescence when I can. And the reason that we get that is carbon dioxide gas has been produced. I should say the reason we get the silver mirror before is we are getting a precipitate of solid silver, and the red precipitate is a precipitate of copper 1 oxide. And last of all, primary or secondary alcohols, we might want to prove that we've still got some left over, or we might just be asked what would we observe in the experiments that we've just been describing on the previous pages. If you were doing a small test tube reaction, you would use acidified potassium dichromate, so acidified CH₂ₙ and it needs to be acidified, and then we warm it gently, and the colour will change from orange for the acidified potassium dichromate, and it would go green, proving that we have got an alcohol present. Alternatively, you might not want to say acidified potassium dichromate, you might want to say potassium dichromate and sulfuric acid, because that is the acid of choice every time, so put brackets around the acidified on there. Last of all, we do make ketones in oxidation reactions sometimes, but for A-level chemistry, there isn't actually a reagent that you need to know. There are reagents that you can use to test for the general presence of carbonyl groups, such as Brady's reagent, but that isn't on your test. So there is no proof for a ketone that you need to know about. And so what you would do in the exam is you would use Fehling's reagent and you would warm it, and you would see no visible change. And so what you've done there is you've proven that it's not an aldehyde. And you could use Tollen's reagent as well in the exact same way, proving that it wasn't an aldehyde by observing no visible change. So what that means is you aren't proving that it is a ketone, you're proving that it is not an aldehyde. And so exam questions might ask you to distinguish between an aldehyde and a ketone, in which case you say one would give a brick red precipitate with Fehling's warmed and the other would give no visible change. Alternatively, you might be proving that there is no carboxylic acid present in your product, so proving that you have only oxidized partially, and you would prove that by adding sodium carbonate powder or solution, or I guess sodium hydrogen carbonate as well would work, and you would be proving that there wasn't a carboxylic acid there by proving that there was no effervescence produced. Okay, that's the end of this video on alcohols. We've got one last organic video, organic analysis, and that will finish year 1 organic chemistry altogether. So well done everybody, hope that was useful, and I'll see you next time. Bye bye.